Hello students, welcome to EPG Pathshala. I am Dr. P.K. Aluwalia from Physics Department, Himachal Pradesh University, Shimla. Today, we are going to discuss about the module Ensemble Theory, Quantum, Part 3, Ideal Bose Gas Applications, Photon Gas, Phonon Gas, and Liquid Helium-4 from paper Statistical Mechanics. This module has been developed for postgraduate level as per the following subtopics: thermodynamics of a photon gas, which involves chemical potential of a photon gas, blackbody radiation as a photon gas, calculation of thermodynamics properties of the blackbody radiation, Planck's law, Rayleigh Jeans approximation, Wien's approximation, energy density, Stefan-Boltzmann law, grand partition function of the photon gas, Helmholtz free energy, entropy, and specific heat at constant volume, and adiabats of a photon gas. We also look at vibrational models in solids, a Phonon gas, Debye model involving Debye spectrum, internal energy, heat capacity of solids at low temperature, and helium-4, a fluid with macroscopic quantum properties, in which we will cover liquefaction of helium and phase diagram of helium-4, some other characteristic properties of helium-2, two fluid models of helium-4, namely TISA two-fluid model and Landau's model. We will also, for them, look at thermodynamics of photon-proton gas through two cases, phonon case and proton case. We will also cover initial mass density of the moving phonon-proton gas, physical interpretation of photon-proton gas spectrum, and critical velocity and Landau criterion for superflow. After studying this module, you shall be able to understand three very important applications of Bose-Einstein statistics to three very interesting problems of modern physics, namely blackbody radiation spectrum, specific heat of solids, and superfluid nature of helium-2. You will be able to look at radiation in a blackbody cavity as a photon gas, a very special case of Bose gas with zero mass and zero chemical potential. You will be able to derive thermodynamical properties of photon gas with Planck's radiation law, grand partition function, Helmholtz free energy, entropy, and specific heat at constant volume and its adiabats. You will be able to understand that quantized elastic vibrations of a crystal can be modeled as a collection of harmonic oscillators and a Bose gas of quasi-particles called phonons. Derive using Debye model the phonon density of state, the so-called Debye spectrum, internal energy, and Debye's T-cube law of specific heat of a solid. Appreciate the phase diagram of liquid helium-4, a quantum liquid. You will be able to comprehend that liquid helium-4 is a bosonic system leading to two liquid phases, one above transition temperature called helium-1 and other below transition temperature called helium-2. List characteristic properties of liquid helium-2 with lambda transition in specific heat, very large heat conductivity, zero viscosity below critical velocity, creeping of liquid helium-2 in the superfluid phase along the walls of the container, Androni-Shvili's experimental evidence that helium-2 below transition temperature has two fluid components, normal and superfluid. You will be able to understand two-fluid model of helium-2 through two distinct approaches of TISA involving Bose condensed phase and non-condensed phase in Landau's phenomenological phonon-proton gas model with use of the idea of two types of quasi-particles, low-lying excitations, termed phonons and rotons. Derive thermodynamic properties of photon-roton gas model of liquid helium-2. Derive inertial mass density for phonon-roton gas and its physical interpretation. Understand the concept of critical velocity and find Landau criterion for superflow. In this module, we look at three very interesting problems of great physical significance which engaged best physics to understand their basis and which contributed immensely in shaping modern physics in the 20th century. First problem corresponds to blackbody radiation spectrum, an ideal photon gas, and the second corresponds to the problem of heat capacity of solids, an ideal phonon gas, and the third corresponds to lambda transition and superfluidity in helium-4. To understand blackbody radiation spectrum, it will be treated as a photon gas belonging to the category of massless boson gas in which total number of bosons is not conserved. To understand heat capacity of solids, we look at solids made up of a quantized lattice vibration in the Debye model consisting of quasi-particle excitations called phonons. The helium-4 problem attracted giants in physics including Fritz London, Kiesom, Laszlo Tisza, Lev Davidovich Landau, N. Bogligov, and Richard Phillips Feynman, and is still engaging researchers to understand its intricacies in the context of phase transition. We look at it through two-fluid model of Tisza and phenomenological two-fluid model of Landau involving photon-roton spectrum. Thermodynamics of a photon gas. A photon gas belongs to the category of massless boson gas in which total number of bosons is not conserved. A photon gas is characterized by the presence of a quantum vacuum. It is a result of quantization of the electromagnetic field. Photons do not interact with each other, and therefore an isolated collection of photons cannot come to the equilibrium because they cannot exchange energy among themselves. Photons can interact with matter, exchange energy and momentum, and come to equilibrium. Photons are massless particles and these obey a linear dispersion relation. Epsilon is equal to C times P is equal to C h bar k is equal to h bar omega, where C is velocity of light, P is momentum, k is wave vector, and omega the angular frequency. The most famous example of a photon gas is encountered in the study of blackbody radiation, whose spectrum at the turn of 19th century was the biggest puzzle in physics and turned out to be a precursor to quantum mechanics. A blackbody radiation at a given temperature T is a result of an electromagnetic radiation in thermodynamic equilibrium with matter. 3K microwave cosmic radiation background discovered by Penzias and Wilson is an example of blackbody radiation confined in the universe acting as a cavity. So first of all, we will look at chemical potential of a photon gas. In Bose-Einstein distribution formula, F epsilon is equal to 1 upon e raised to power epsilon minus mu upon kBt minus 1. Recall, mu appears because of the constraint of particle number conservation. So when requirement of number conservation is no longer needed, we do not require Lagrange's undetermined multiplier needed for such a constraint, and chemical potential must be chosen as 0. Furthermore, photons have no constraint of charge conservation, lepton number conservation, etc. needed to be imposed in the study of systems of photons. As a result of this, the Bose-Einstein distribution function takes a simple form. F epsilon is equal to 1 upon e raised to power epsilon upon kBt minus 1, where epsilon can be treated as a function of either omega or k, such that it can be written as f omega is equal to e raised to power h bar omega by kBt minus 1. Another interesting characteristic which needs to be noted is that photons have two polarization directions, that is, independent internal states because electromagnetic radiations are transverse in nature. Let us focus our attention on blackbody radiation, which is an example of a photon gas. A blackbody radiation cavity can be considered as having volume V and equilibrium temperature. To understand the thermodynamics of the blackbody radiation, historically, two parallel approaches were followed. First treated blackbody cavity as made up of a collection of distinguishable harmonic oscillators with quantized energy Ni plus half multiplied by h bar omega I, where Ni is equal to 0, 1, 2, 3 and omega I being the angular frequency of the harmonic oscillator. In the second approach, cavity was treated as filled with a gas of identical particles called photons with energy h bar omega I. Here we follow the second approach, which treats the blackbody cavity as an ideal Bose gas made up of photons and look at its thermodynamics, an approach which was followed by Bose. So let's see whether we can derive Planck's law with this approach. In fact, Bose asked the following question: what is the probability of occupation of an energy level epsilon s by ns photons, the statistics of energy levels being Boltzmannian type? The mean value of ns and epsilon s, however, turns out to be equal to summation over ns is equal to 0 to infinity ns e raised to power minus ss h bar omega s divided by kBt divided by summation over ns is equal to 0 to infinity e raised to power minus ns h bar omega s upon kBt is equal to 1 upon e raised to power h bar omega s divided by kBt minus 1, and the mean value of epsilon s is equal to h bar omega s multiplied by the mean value of ns, which is equal to h bar omega s divided by e raised to power h bar omega s upon kBt minus 1. The number of photon states with momenta lying between p is equal to h bar omega upon c and p plus dp is equal to h bar omega plus d omega by c can then be written as gp dp is equal to 2 times v upon h cube multiplied by 4 pi p square dp is equal to g omega d omega is equal to 2 times v upon h cube 4 pi h bar omega by c whole square h bar d omega by c is equal to v omega square d omega divided by pi square c cube. Here, factor of 2 takes care of two transverse polarization modes. Therefore, number of photons per unit volume whose frequency lies between omega and omega plus d omega can be written as n omega is equal to 1 upon pi square c cube multiplied by omega square upon e raised to power h bar omega by kBt minus 1 multiplied by d omega. The energy density of radiation lying between omega and omega plus d omega is u omega t d omega is equal to n omega h bar omega is equal to h bar upon pi square c cube omega cube upon e raised to power h bar omega by kBt minus 1 into d omega. This is exactly the Planck's formula. To look at its physical significance, we can express it in dimensionless form by putting h bar omega by kBt is equal to x such that d omega is equal to kBt upon h bar into dx. Therefore, ux dx is equal to kBt raised to power 4 upon h bar cube pi square c cube into x raised to power 3 divided by e raised to power x minus 1 dx is equal to a function phi of temperature and a function delta of x, where x is equal to h bar omega by kBt. Here, delta x is equal to x cube upon e raised to power x minus 1 is the spectral distribution of energy of the blackbody radiation. Now let's see whether we can get the two famous approximations known as Rayleigh-Jeans approximation and Wien's approximation. So first, the Rayleigh-Jeans approximation. For x very much less than 1, the spectral density delta x reduces to delta x is equal to x raised to power 3 divided by e raised to power x minus 1, which can be approximated as x raised to power 3 divided by 1 plus x minus 1, which is equal to x square. This corresponds to long wavelength limit and represents the Rayleigh jeans classical result. It agrees with the experimental results only at low frequencies. The discrepancy in the experimental result and Rayleigh jeans approximation means that the blackbody cavity has infinite energy and was called ultraviolet catastrophe. Now let us look at Wien's approximation. For x very much greater than 1, spectral density delta x reduces to delta x is equal to x cube upon e raised to power x minus 1, approximately equal to x raised to power 3 divided by e raised to power x is equal to x raised to power 3 into e raised to power minus x. This corresponds to short wavelength limit and represents the Wien's classical result. This formula describes the experimental data nicely in the regions of high frequency. A plot of ux versus x at constant t is shown in figure 1 for the three cases: Planck's law, Rayleigh jeans approximation, and Wien's approximation. The first one is shown as a solid curve. The second one is shown with the help of dashed lines, and the third one is shown as dotted lines. The first one corresponds to the Planck's law. The second one corresponds to Rayleigh jeans law, that is x very much less than 1, and the third one corresponds to Wien's approximation, that is x very much greater than 1. Let us now try to calculate the total energy density. To find the total energy density ut, we must integrate 9 over all frequencies, which, using a standard integral formula, integral from 0 to infinity x raised to power 3 e raised to power x minus 1 dx is equal to pi raised to power 4 upon 15 gives ut is equal to integral from 0 to infinity ux dx is equal to kbt raised to power 4 divided by h bar cube pi square c cube integral from 0 to infinity x raised to power 3 divided by e raised to power x minus 1 dx is equal to kbt raised to power 4 divided by h bar cube pi square c cube multiplied by pi raised to power 4 upon 15 is equal to kb raised to power 4 upon h bar cube c cube multiplied by pi square upon 15 multiplied by t raised to power 4, or ut is equal to a constant multiplied by t raised to power 4, where constant a is equal to kb raised to power 4 divided by h bar cube c cube multiplied by pi square upon 15. The energy density of the cavity radiation is therefore proportional to 4th power of the temperature T. Now let's look at the Stephan-Boltzmann law. Since the blackbody radiation cavity is completely isotropic, the energy radiated per unit solid angle is ut divided by 4 pi, and over a solid angle d omega will be ut upon 4 pi multiplied by d omega, where d omega is equal to 2 pi sine theta d theta. So the energy coming out per unit area per unit time in direction theta to the normal is the amount of energy contained in a volume element of the height c cos of theta and base of unit area. So the energy coming out per unit time per unit area, also called total emissive power RB, is ut upon pi c cos of theta 2 pi sine of theta d theta integrated over hemisphere. That is, RB is equal to ut upon 4 integral from 0 to pi by 2 c 2 cos of theta sine of theta d theta is equal to c u as a function of t divided by 4 is equal to a c t raised to power 4 divided by 4 is equal to sigma t power 4, where sigma is equal to c kb power 4 upon 4 h bar cube c cube into pi square upon 15 is the Stephan-Boltzmann constant. Equation 14 constitutes Stephan-Boltzmann law. This can be easily verified in the laboratory. Wien's displacement law. The energy density of radiation c upon 4 u as a function of omega and t versus omega over a hemisphere is using equation 9 can be plotted as in figure 2. At different temperatures, we note that there is a characteristic maximum in energy density of radiation as the temperature increases. Maxima shifts to higher frequencies, and this is the famous Wien's displacement law. Now let us try to evaluate the grand partition function of the photon gas. To study the thermodynamics of photon gas with Z is equal to 1, we can calculate its partition function using the relation log of curly Q as a function of V and T is equal to PV upon kBT is equal to minus summation over epsilon log of 1 minus e raised to power minus epsilon upon kBT, where curly Q as a function of V and T is the grand partition function. Using 15, summation over epsilon can be converted into an integration, so that log of curly Q as a function of V and T is equal to PV upon kBT is equal to minus 8 pi V upon h cube c cube integral from 0 to infinity log of 1 minus e raised to power minus epsilon upon kBT epsilon square d epsilon. Integrating by parts, we get log of curly Q as a function of V and T is equal to PV upon kBT is equal to plus 8 pi V upon 3 h cube c cube 1 upon kBT integral from 0 to infinity epsilon cube upon e raised to power epsilon by kBT minus 1 d epsilon. Putting epsilon by kBT is equal to x, we get using standard integral from 0 to infinity x cube dx divided by e raised to power x minus 1 is equal to pi raised to power 4 divided by 15. Log of curly Q as a function of V and T is equal to PV upon kBT is equal to plus 8 pi V upon 3 h cube c cube multiplied by kBT raised to power 4 divided by kBT integral from 0 to infinity x cube dx upon e raised to power x minus 1 is equal to plus 8 pi raised to power 5 V upon 45 h cube c cube into kBT raised to power 4 divided by kBT. Therefore, PV is equal to plus 8 pi raised to power 5 V upon 45 h cube c cube multiplied by kBT raised to power 4 is equal to 1 upon 3 UT. This result matches with the result from radiation theory, according to which pressure of the radiation is 1/3 of the energy density. Now we can calculate Helmholtz free energy, entropy and specific heat at constant volume. Recalling formula for Helmholtz free energy, F is equal to mu n minus PV, and noting that for a photon gas mu is equal to 0, we get F is equal to minus PV is equal to minus 1 upon 3 UT. Now entropy can be easily obtained as S is equal to U minus F upon T, which is equal to 4 upon 3 UT upon T is equal to B times V T raised to power 3, where B is a constant. Hence, specific heat at constant volume can be obtained as Cv is equal to T times partial derivative of S with respect to T at constant volume is equal to 3 times B times V T raised to power 3 is equal to 3S. Now let us calculate adiabats of a photon gas. For a reversible adiabatic change in the photon gas, entropy is a constant, and therefore from 23 V T raised to power 3 is equal to constant, and also from 20 P is equal to constant times T raised to power 4. Combining 24 and 25, we get PV raised to power 4 by 3 is equal to constant, which is the equation for the adiabat of a photon gas. Now we come to another problem which involves bosons. We intend to look at a phonon gas, particularly made up of vibrational modes in solids. So, another example of a Bose gas arises in crystalline solids, which in many ways is similar to a photon gas as encountered in the case of blackbody radiation, which is treated as a collection of quanta of electromagnetic radiation energy called photons. Since crystalline solid can also be treated as a collection of quanta of sound energy called phonons. Phonons are the quasi-particles associated with the quantization of the elastic vibrations of atoms of a solid about their mean position, representing collective oscillations in the system. In this way, thermal vibrations of a lattice are reduced to an ideal gas of phonons, which are enclosed in a space occupied by the volume of the crystal. The model of a solid treating atoms at their mean position as a collection of uncoupled harmonic oscillators of same frequency was first of all proposed by Einstein in 1907 to explain the specific heat of solids at low temperatures. Later in 1912, Debye extended Einstein's model by relaxing the condition of the same frequency of each harmonic oscillator to assuming that a crystal has a continuum of frequencies starting from 0 to some maximum limit. Earlier, we have already discussed Einstein's model. Here we will discuss Debye's model using concept of Phonon gas. Thermal equilibrium in the gas is established by a mechanism of phonon collisions. The number of phonons depends on the equilibrium conditions and is not conserved. Therefore, just like photon gas, number of phonons is not conserved in a phonon gas. Depending upon the changes in the lattice energy, phonons can be created or annihilated. Since Hamiltonian is a sum of independent harmonic oscillator terms called normal modes with energy of the form En is equal to n plus half h bar omega I, where omega I depends on the normal mode I, let solid has n atoms. Since each atom has 3 degrees of freedom, the total number of normal modes is 3n. Total energy then is E summed over all Ni is equal to summation over I is equal to 1 to 3n Ni plus half h bar omega I, where half h bar omega I is the 0-point energy. So what is there in the Debye model? Debye proposed that to know omega I, assume the solid behaves approximately like an elastic continuum. With dispersion relation, omega is equal to Cs times k, where Cs is the speed of sound in the solid. The wave numbers kx, ky and kz have the values given by the standing waves in the crystal if we assume a cubic lattice. Omega I is equal to Cs times the magnitude of the wave vector k, with kxi is equal to pi upon L nxi, kyi is equal to pi upon L nyi, kzi is equal to pi upon L nzi, where nxi, nyi and nzi are the energy level index of the ith harmonic oscillator. For every value of omega I, there are 3 distinct modes, 2 of which corresponds to transverse waves and 1 of longitudinal waves, also called optic and acoustic modes respectively. Debye assumed that the allowed frequencies are those sets of non-negative integers which are the coordinates of points lying inside a sphere of radius such that total number of such points equal n and each point contributes 3 modes. Because each of nxi, nyi, nzi are positive, they are restricted to only 1/8 part of the sphere, that is 1 octant only. That is, each omega I is less than or equal to omega d, which implies that the total number of points nx, ny, nz equal n, with nx square plus ny square plus nz square is less than or equal to L square omega d square upon pi square Cs square. This leads to 2 important implications. First, the fact that there is an upper limit omega d for the frequency, it is result that atoms are arranged on a lattice so that wavelength cannot be smaller than the distance between 2 neighboring atoms. Secondly, by taking a sphere in k space, it is assumed that the elastic medium is isotropic. Omega d can be found by setting the total number of modes equal to 3n, where n is the number of atoms in the crystal. Therefore, 3n is equal to integral from 0 to kd 3 times 1 upon 8 multiplied by 4 pi k square dk multiplied by L upon pi whole cube is equal to 3v integral from 0 to kd 4 pi k square dk into 1 upon 2 pi whole cube is equal to v times kd cube divided by 2 pi square is equal to v times omega d cube divided by Cs cube upon 2 pi square. Then omega d is equal to 6 pi square Cs cube multiplied by n upon v whole raised to power 1 by 3. Now we will look at device spectrum. Also, if g omega is defined as number of phonon states per unit frequency range called density of phonon states, then the total number of states integral of g omega d omega is equal to 3n is equal to 12 v pi upon Cs cube into 1 upon 2 pi whole cube integral over omega square d omega. Comparing the left and right hand side, we get g omega is equal to 12 v pi upon Cs cube multiplied by 1 upon 2 pi whole cube omega square, which is equal to 9n upon omega d cube into omega square. This spectrum is called device spectrum, which matches well with the low frequency acoustic modes of real systems. However, it goes astray at high frequency range corresponding to optic modes. Now let's look at internal energy. If we assume that for each mode sound velocity is same, then the internal energy is given by U is equal to summation over I is equal to 1 to n h bar upon 2 omega I plus summation over I is equal to 1 to n h bar omega I divided by e raised to power h bar omega I upon kBt minus 1, which can be written further in continuum approximation or Debye approximation as U is equal to U naught plus 3 times V upon 2 pi whole cube integral from 0 to kd h bar omega k divided by e raised to power h bar omega k upon kBt minus 1 into 4 pi k square dk is equal to u0 plus 3 times v h bar upon 2 pi square Cs cube integral from 0 to omega d omega cube upon e raised to power h bar omega by kBt minus 1 d omega. Here factor 3 appears because of 3 modes of vibration. Let x is equal to h bar omega by kBt is equal to theta t, then we can write u is equal to u naught plus 3 kb raised to power 4 t power 4 into v divided by 2 pi square Cs cube h bar cube integral from 0 to theta d upon t x cube upon e raised to power x minus 1 dx. For very low temperatures, theta d upon t approaches infinity, and the integral from 0 to infinity x cube upon e raised to power x minus 1 dx is equal to pi raised to power 4 upon 15. Therefore, u will be equal to u naught plus 3 times kb raised to power 4 t power 4 into v divided by 2 pi square Cs cube h bar cube into pi raised to power 4 upon 15 is equal to u0 plus a t raised to power 4, where a is equal to kb raised to power 4 pi square v upon 10 times Cs cube h bar cube. Heat capacity of solids at low temperature. Heat capacity can be obtained as specific heat at constant volume is equal to partial derivative of internal energy with respect to temperature at constant volume, which is equal to 4 times A times T cube. This is the famous Debye T cube law for specific heat of solids at low temperatures. Now we try to look at a fluid made up of helium-4 with macroscopic quantum properties. Therefore, let us first of all look at very interesting properties of helium-4. Helium is an element which was discovered first on Sun through the study of solar spectrum during a total solar eclipse in India in 1868 by a French astronomer Jules Janssen, and was later discovered on the Earth by William Ramsay. It has 2 isotopes, one of which, helium-3, is a fermion and the other, helium-4, is a boson. Helium-4 has even number of protons, electrons and neutrons and is most stable. It is ejected as positively charged alpha particle in radioactive decay process called alpha decay, and was used by Rutherford as a projectile to discover nucleus, leading to the development of nuclear model of atom. liquefaction of helium and phase diagram of helium-4. Kamerlingh Onnes was the first person who succeeded in liquefying it in 1908 and found that as the temperature falls, the density of liquid helium is maximum at around 2.2 degrees Kelvin, which falls as one goes below this temperature. It is one of those elements which cannot be solidified under normal pressure and only with the application of a pressure of 25 atmosphere that it solidifies. Non-solidification under normal pressure suggests that it is a weakly interacting system, being a noble gas. Below a temperature of 2.17 degrees Kelvin, it is a superfluid, that is, its viscosity is almost zero and has high thermal conductivity. And this turns out to be representing a new liquid phase of helium-4, which can be perceived visually as was first observed by W. H. Kizom and M. Wolfke in 1927. W. H. Kizom and M. Wolfke gave the nomenclature helium-1 to the stable liquid phase at a temperature above transition temperature and helium-2 to the stable liquid phase below transition temperature. It was further studied by Kapitsa and Allen and Meissner, who in 1938 proposed the name superfluid to the frictionless flow of helium-2. Phase diagram of helium-4 is shown in figure 3, where very clearly we can see liquid helium-1 phase, liquid helium-2 phase, and solid helium phase. There are some other characteristic properties of liquid helium-2. These are: number 1, liquid helium-4 as seen in its phase diagram undergoes a transition at 2.18 degrees Kelvin when liquid helium-2 appears. The signatures of this transition can be observed by specific heat measurement as shown in figure 4. Since the shape of the curve shown in the figure resembles Greek letter lambda, so this point is also called lambda point. The specific heat curve has a very interesting resemblance with the specific heat of the ideal Bose gas shown in the figure 5 and suggests that to explain lambda transition, Bose-Einstein condensation must play some role. Empirically, around lambda point, this behavior is given by Cv is equal to A plus B log of T minus T lambda at T less than T lambda and A dash plus B log of T minus T lambda for T greater than T lambda. Number 2, helium-2 doesn't boil, which means that heat conductivity of helium-2 is very large, effectively infinite. Helium-2 is a superfluid, that is, it has a zero viscosity, and below critical velocity Vc, helium-2 flows through a thin capillary called superleak with zero resistance. With decrease in diameter of the capillary, critical velocity increases. However, if a cylinder is placed in liquid helium-2 and rotated in it, there is a momentum transfer from the rotating cylinder to the helium, revealing that viscosity is not zero. Helium-2 shows thermomechanical effect. In the first case, if two containers A and B of the helium-2 with density ρ are connected by a fine capillary at a constant temperature, then a superflow through the capillary occurs until the pressure difference delta P doesn't become equal to ρ times S times delta T, where S is the specific capacity. The pressure difference leading to temperature difference is thermomechanical effect. If one of the containers is thin tube, it shows a fountain effect. Helium-2 also shows mechanocaloric effect. If two containers A and B of the helium-2 are kept at constant pressure, and if mass flows from A to B, container B cools. This is mechanocaloric effect. The cooling of container B can be expected if mass transported has zero entropy and zero temperature. Also, if helium-2 is taken in a beaker and kept at a temperature below the lambda point, it will rise up the sides of the beaker and spill out of it, as shown in the adjoining figure. Andronikashvili performed a very interesting experiment to show that helium-2 indeed has two kinds of fluids. He took a container having helium-2 below lambda point and suspended by a torsion fiber. He measured the period of torsional oscillations at different temperatures. The disk spacing in the system was such that at the period of oscillation, disk system was completely coupled with normal component of the fluid and superfluid component remained uncoupled. This implied that normal fluid is contributing to the moment of inertia of the disk system, whereas superfluid component has no contribution. This experiment provided a proof of dependence of normal fluid density on the temperature as shown in the figure 6. Fit for the experimental data shown in the figure is given by rho n upon rho is equal to T upon T lambda raised to power 5.6 for T less than T lambda and 1 for T greater than T lambda. So to understand this superfluidity, there were two famous physicists who gave a model called two-fluid model of liquid helium-4, one of whom was Laszlo Tisza and the other was Lev de Landau. Tisza's two-fluid model. It was Fritz London who for the first time pointed to the connection of superfluidity to Bose-Einstein condensation as found in the study of an ideal Bose gas. He also saw a conceptual connection of superfluidity with superconductivity. Later, London with Tisza, a Hungarian physicist, proposed a phenomenological two-fluid model for helium-2, according to which it is a mixture of Bose condensed and non-condensed phases called superfluid and normal fluid. According to this model, to explain superfluidity with zero viscosity and normal fluid with normal viscosity, one needs to assume that helium-2 is a very close mixture of two fluids, one with zero viscosity and with density rho s, and other with normal viscosity and density rho n. Also, if the liquid flows, Tisza proposed characteristic velocities Vn and Vs respectively to normal fluid and superfluid helium. Furthermore, it was assumed that the mass density rho and the velocity v were assumed to be given by rho is equal to rho normal plus rho s and rho into v is equal to rho normal into v normal plus rho superfluid into v superfluid. In this two-fluid model, propagation of a longitudinal wave, the so-called sound wave, meant a sinusoidal oscillation of rho normal and rho superfluid in phase with each other, leading to total mass density varying sinusoidally, leading to an ordinary sound wave, which is a result of pressure variation. However, there is a possibility of a different mode of oscillation in which normal fluid and superfluid oscillate out of phase by 180 degree such that total mass density remains constant, and obviously this cannot be ordinary sound wave but is a result of sinusoidal variation of specific entropy, that is entropy per unit mass, because superfluid doesn't have entropy. This new method of oscillation can be generated by local heating of helium-2. The temperature gradient so produced propagates not by diffusion but like a wave with characteristic velocity, leading to the concept of second sound, which is not a mechanical wave but a thermal wave. By applying thermodynamics alone, Tisza, through this model, could get results quantitatively for all the observed phenomena like fountain effect and mechanocaloric effect. But to account for superfluidity, it was later found that it is not enough to treat fluid as an ideal Bose gas, but should be treated as a weakly interacting Bose gas. Now let us look at Landau model. Study of helium-4 is an interesting case study of physics looking at the two-fluid model from completely different points of view. In 1941, Landau gave an entirely different microscopic interpretation of the two-fluid model. According to him, it is not the Bose-Einstein condensation which is responsible for strange properties of helium-4, and proposed for such a quantum system a spectrum called Bose spectrum of elementary excitations omega k, which can be found by neutron scattering as shown in figure 7, which is represented by the relations h bar omega k is equal to h bar ck, k very much less than k0, and is equal to delta plus h bar square into k minus k naught whole square divided by 2 sigma at k approximately equal to k0, where c is the velocity of sound and m is the mass of helium atom. C is equal to 239 plus minus 5 meters per second. Delta by k is equal to 8.65 plus minus 0.04 k, and k naught is equal to 1.92 plus minus 0.01 per angstrom, and sigma upon m is equal to 0.16 plus minus 0.01 are the experimentally determined parameters called Landau parameters. In fact, figure 7 gives us a schematic excitation spectrum of helium-2 showing linear phonon-like spectrum with dotted lines and Landau's Roton spectrum with a minimum. Solid triangles show Yarnell et al.'s neutron scattering data at a temperature of 1.1 K. According to Landau, there is a very subtle quantum mechanical difference between the normal fluid and superfluid. Normal fluid consists of helium-4 atoms in thermally low-lying excited states, whereas superfluid consists of helium-4 atoms condensed in the ground state. The spectrum for K very much less than K0 is phonon-like, that is linear, whereas the part of the spectrum at K is equal to K0 was given the name Roton-like, which is a quasi-particle with sigma as its effective mass and requires a minimum energy delta for its creation, that is, has to cross an energy gap of delta for its creation. Now let us try to have a look at thermodynamics of phonon-roton gas. By a glance at the excitation spectrum of helium-2, one finds three regions of interest. At sufficiently low temperature, spectrum is linear like that of phonons, low-lying excitations, that is EP is equal to Cp. Around 0.5 K, the other excitations corresponding to rotons also appear with wave vector around K is equal to K0 or momentum P is equal to P0. Between 0.5 K and 1 K, both phonons and rotons influence the behavior of helium-2. Above 1 K, only rotons influence the behavior and phonons are not important. That is, EP is equal to delta plus P minus P naught whole square divided by 2 sigma. Now since energy spectrum of helium-2 is continuous, phonons and rotons follow Bose-Einstein statistics. Also like photons, their number is not conserved and hence have chemical potential mu is equal to 0. So the mean occupation number of phonons or rotons is given by NPs is equal to 1 upon e raised to power EP upon kBt minus 1. The Q potential of the phonon-roton spectrum system is given by Q as a function of Vt is equal to Pv upon kBt is equal to minus summation over P log of 1 minus e raised to power minus Ep upon kBt, such that Helmholtz free energy F is given by F is equal to kBt summation over P log of 1 minus e raised to power minus Ep upon kBt. Let us therefore look at the two cases, that is the phonon case and the roton case separately. The internal energy of the liquid is given by E phonon is equal to sigma P, expectation value of Np multiplied by Ep, is equal to integral from 0 to infinity Ep upon e raised to power Ep upon kBt minus 1 multiplied by V dqp upon 2 pi h bar whole cube is equal to V times integral from 0 to infinity Ep upon e raised to power Ep upon kBt minus 1 multiplied by 4 pi p square dp upon 2 pi h bar cube, or E phonon is equal to V times integral from 0 to infinity Pc upon e raised to power Pc upon kBt minus 1 into 4 pi p square dp upon 2 pi h bar whole cube. Put Pc upon kBt is equal to x. 48 becomes E phonon is equal to 4 pi V kb power 4 t power 4 upon h cube c cube integral from 0 to infinity x cube upon e raised to power x minus 1 dx is equal to 4 pi V kb raised to power 4 t power 4 upon h cube c cube multiplied by pi raised to power 4 upon 15 is equal to 4 pi raised to power 5 V kb raised to power 4 t raised to power 4 divided by 15 h cube c cube. Hence, specific heat at constant volume can be calculated as Cv corresponding to the phonon part is equal to partial derivative of E phonon with respect to temperature is equal to partial derivative of 4 pi raised to power 5 V kV raised to power 4 t power 4 divided by 15 h cube c cube with respect to temperature is equal to 16 pi raised to power 5 V kV raised to power 4 t raised to power 3 upon 15 h cube into c cube. Let us now focus our attention on Proton case. Noting that e raised to power ep upon kBt is equal to e raised to power delta plus p minus p naught upon 2 sigma square divided by kBt is equal to e raised to power delta by kBt e raised to power p minus p naught whole square divided by 2 sigma upon kBt is such that the term e raised to power delta by kBt is very large compared to 1. Therefore, the mean value of Np is equal to 1 upon e raised to power ep upon kBt minus 1 is approximately equal to e raised to power minus ep upon kBt. From 45 we note that Pb upon kBt is equal to the average value of the number of particles, that is equilibrium number of protons, is equal to minus summation over p log of 1 minus e raised to power minus ep upon kBt, which is approximately equal to summation over p e raised to power minus ep upon kBt. Converting summation into an integral, the average number of particles n can be written as n average is equal to summation over p e raised to power minus ep upon kBt is equal to v e raised to power minus delta upon kBt integral from 0 to infinity e raised to power minus p naught whole square upon 2 sigma kBt multiplied by 4 pi p square dp upon 2 pi h bar whole cube. Put p minus p naught whole square divided by 2 sigma kBt is equal to x square, then p is equal to p naught plus 2 sigma kBt raised to power half x, and dp is equal to 2 sigma kBt raised to power half dx, and 53 becomes equal to 4 pi v upon h cube 2 sigma kBt raised to power half e raised to power minus delta upon kBt integral from 0 to infinity e raised to power minus x square p naught square into 1 plus 2 sigma kBt raised to power half x upon p naught whole square dx. Once again noting that 2 sigma kBt upon p naught square is very much less than 1, the linear and quadratic terms in 1 plus 2 sigma kBt raised to power half multiplied by x upon p naught whole raised to power 2 are negligible. Also, without altering much the value of the integral, lower limit can be extended to minus infinity. Therefore, we only need to integrate integral minus infinity to infinity e raised to power minus x square dx, a standard integral equal to square root of pi. Hence, the equilibrium number of protons n bar is equal to 4 pi p naught square v upon h cube 2 sigma pi kBt raised to power half e raised to power minus delta by kBt. Now we can calculate other thermodynamic properties as well. Helmholtz free energy of the Proton gas is then given by F is equal to minus PV is equal to minus n bar kBt is equal to minus 4 pi p naught square V upon h cube 2 sigma kb raised to power half t raised to power 3 by 2 e raised to power minus delta by kBt, which is proportional to t raised to power 3 by 2 e raised to power minus delta upon kBt. Also, entropy S is equal to minus delta F upon delta T, where F is Helmholtz free energy, which is equal to 4 pi P naught square V upon H cube into 2 sigma kb raised to power half T raised to power 3 by 2 e raised to power minus delta upon kbt multiplied by 3 upon 2t plus delta upon kbt square is equal to minus F times 3 by 2t plus delta upon kbt square, which is equal to n bar kb multiplied by 3 by 2 plus delta by kbt. Internal energy U is equal to F plus Ts can now be obtained as U is equal to F plus Ts is equal to average number of protons n bar multiplied by half kbt plus delta. The specific heat of Proton gas then is given by Cv is equal to partial derivative of U with respect to T at constant volume, which is nothing but partial derivative of n bar multiplied by half kbt plus delta with respect to temperature is equal to n bar kb multiplied by 3 by 4 plus delta by kbt plus delta by kbt whole square, or Cv is equal to 4 pi P naught square multiplied by V upon H cube multiplied by 2 sigma kbt raised to power half e raised to power minus delta upon kbt multiplied by kb whole multiplied by 3 by 4 plus delta by kbt plus delta by kbt whole square. It is obvious that Cv approaches 0 exponentially as T approaches 0, an interesting result. Now, there is another very interesting feature which we must look at, which corresponds to inertial mass density of the moving phonon roton gas. Inertial mass density is a very interesting parameter to understand the low temperature behavior of liquid helium-4. This is effectively the inertial mass rho 0 corresponding to phonons associated with a phonon gas, and inertial mass rho 0 roton associated with a roton gas. For understanding this, we need to consider a photon roton gas in mass motion observed in a frame of reference with respect to which motion is being observed, and get a relationship between momentum p of the photon or roton gas and velocity v of its mass motion. Furthermore, we note following constraints on the system. Since the total number of phonons or rotons is not constant, so chemical potential is 0 since there is no constraint of particle number conservation. Secondly, the total energy E must be conserved. Thirdly, the total momentum P must also be conserved. So the mean occupation number of phonon or roton level epsilon P is given by 1 upon e raised to power beta epsilon plus gamma dot P minus 1, where beta and gamma are undetermined multipliers, with beta is equal to 1 upon kbt and gamma is equal to minus beta v, where v is the drift velocity of the phonon oblique roton gas. Therefore, the mean occupation of the phonon oblique roton state is given by 1 upon e raised to power beta epsilon minus v dot p minus 1. For small v, n epsilon minus v dot p can be expanded as a Taylor series in v, or we can also write this as equal to n epsilon minus v dot p partial derivative of n epsilon with respect to epsilon. So the inertial mass density is given by rho naught is equal to m naught upon v is equal to limit v approaching 0 1 upon v integral over n as a function of epsilon minus v dot p into p d cube p upon h cube, which is equal to limit v approaching 0 1 upon v integral over n epsilon minus v dot p partial derivative of n epsilon with respect to epsilon multiplied by p d cube p upon h cube. First term in the integral represents momentum density in the rest frame and hence is identically equal to 0. Thus, rho naught is equal to minus limit v approaching 0 1 upon v integral over v dot p delta n epsilon with respect to epsilon p d cube p h cube, or rho naught is equal to minus limit v approaching 0 1 upon v vp cos of theta partial derivative of n epsilon with respect to epsilon p d cube p upon h cube is equal to minus 1 upon h cube integral of p cos of theta delta n epsilon upon d epsilon p cos of theta 2 pi p square dp sine of theta d theta, or rho naught is equal to minus 2 upon h cube integral of p raised to power 4 partial derivative of n with respect to epsilon dp multiplied by integral from 0 to pi cos square theta sine of theta d theta is equal to minus 4 pi upon 3 h cube integral of p raised to power 4 partial derivative of n epsilon with respect to epsilon dp. The above result can be applied to find inertial mass density for phonon roton gas. Let's look at these two cases separately. Phonon case. For phonon case, recalling epsilon is equal to Pc, we can write 67 as rho 0 corresponding to phonon is equal to minus 4 pi upon 3 h cube integral of p power 4 delta np upon delta pc dp is equal to minus 4 pi 3 c h cube integral of p raised to power 4 partial derivative of np with respect to p dp. This can be integrated by parts as follows. Rho 0 of phonon is equal to minus 4 pi upon 3 c h cube whole multiplied by p raised to power 4 np limit from 0 to infinity minus integral from 0 to infinity 4 pi cube np dp, or rho 0 phonon is equal to 4 pi divided by 3 c h cube integral from 0 to infinity 4 p cube np dp is equal to 4 upon 3 square v multiplied by v times integral from 0 to infinity pc np 4 pi p square dp divided by h cube, which is equal to 4 upon 3 c square v and the average ground state energy of the phonon. From 49, E phonon was equal to 4 pi raised to power 5 V kb raised to power 4 t raised to power 4 divided by 15 h cube c cube, or rho 0 phonon is equal to 16 upon 45 into pi raised to power 5 kb power 4 t raised to power 4 divided by h cube c raised to power 5. Now let us look at the roton case. We recall for the roton case from 51 that n epsilon is approximately equal to e raised to power minus beta epsilon. Therefore, partial derivative of n epsilon with respect to epsilon is approximately equal to minus beta n epsilon. Once again using 67, we have rho 0 of rotons is equal to 4 pi beta upon 3 h cube integral of p raised to power 4 n epsilon dp, which is equal to beta upon 3v into v integral of p square n epsilon multiplied by 4 pi p square dp upon h cube, which is equal to beta upon 3 multiplied by the expectation value of p square n bar upon b, where beta upon 3 multiplied by expectation value of p square is equal to expectation value of p square divided by 3 kbt is the effective mass of the roton. Since the mean value of p square is equal to p naught square and the mean value of number of rotons is equal to 4 pi p naught square v upon h cube multiplied by 2 sigma pi kbt raised to power half into e raised to power minus delta by kbt, we have rho 0 of photon is equal to 4 pi p naught square upon 3 h cube multiplied by 2 pi sigma upon kbt raised to power half multiplied by e raised to power minus delta upon kbt. Now let us try to analyze the fluid inertial mass density and the photon-roton contribution. A comparison of 71 and 73 clarifies the contribution of phonons and rotons towards inertia of the fluid. At very low temperatures, that is T less than 0.3 K, contribution by phonons is dominant and the roton contribution compared to phonon contribution is negligible. As temperature rises to about 0.6 K, the contributions of phonons and rotons becomes comparable. At about 1 K, the roton contribution becomes so dominant that roton density accounts for the density of the normal fluid density, that is rho n. The temperature at which the theoretical value of the normal fluid density rho n becomes equal to the actual density of the liquid helium defines the critical temperature Tc, at which superfluid part of liquid helium disappears indicating phase transition from helium-2 to helium-1. This theoretical critical temperature comes out to be approximately 2.5 degrees Kelvin compared with experimental value of 2.19 K. This is commendable keeping in mind the fact that photon-roton gas discussed here is non-interacting, an assumption which will no longer remain valid at higher temperatures with large number of excitations. The roton effective mass, that is p square upon 3 kBt, is inversely proportional to temperature of the roton gas. However, since Landau had empirically found that effective mass is inversely proportional to temperature, therefore, the mean value of p square for the given excitation does not depend on temperature and hence is constant. It is why this value was denoted above as p naught square. This further necessitates that the mean value of epsilon must increase to take care of the constancy of p naught square and rise of epsilon together. This desires that the energy spectrum of liquid helium-4 must have a minimum at p is equal to p naught. Now, it is worth looking at another very interesting result which actually links critical velocity of the flow and Landau's criteria for superflow. Landau also proposed a criteria to decide whether a given liquid system will undergo a superfluid transition or not. The argument follows by looking at change in energy E is equal to half mv square and momentum p is equal to mv in the fluid, which can be caused by some excitation in the phonon-roton system in accordance with the law of conservation of energy and momentum, such that change in E and change in momentum p are related with each other by the relation delta E is equal to V times delta P. If delta D is because of the creation of an excitation epsilon P, then according to law of conservation of energy, delta E is equal to minus epsilon and delta P is equal to minus P. Then equation 74 leads to epsilon is equal to V times P, which is equal to Vp cos of theta is less than equal to Vp. This inequality implies that for creation of an excitation of energy epsilon, the drift velocity v of the fluid should be such that v is greater than or equal to epsilon upon p. So, if v is less than lowest value of epsilon upon p, there will be no excitation and liquid will maintain its superfluid character. Thus, the criteria for maintaining superfluidity emerges, that is, v is less than vc. This upper limit is called critical velocity of superflow, above which fluid does not remain superfluid. The critical velocity is dependent on the geometry of the channel and its value has been found to lie between about 1.0 into 10 to the power minus 3 meters per second to about 7.0 into 10 to the power minus 1 meters per second. Furthermore, if the excitations correspond to an ideal gas for which epsilon is equal to p square upon 2m, the minimum velocity lies exactly at v is equal to 0. This is a very interesting situation. Every velocity v will lie above v is equal to 0 and hence there will be no velocity for which superflow can be there. Physically, this implies that for Vc to be above 0, system should not behave like an ideal gas and must have an interatomic interaction, that is, gas must be non-ideal. This also points to the fact that an ideal Bose gas can show Bose-Einstein condensation, but it cannot show superfluidity. For superfluidity to be there, Bose gas must be non-ideal. This physical reality led many researchers to look at the problem of superfluidity beyond two-fluid model. N. Bogley-Bob in 1947 looked at this problem as a non-ideal Bose gas and applied second quantization approach and found that energy spectrum from such a system has a quasi-particle excitations whose momentum dependence is a combination of linear and quadratic terms in momentum, that is, epsilon is equal to Cp plus sigma p square, where c is the speed of sound and sigma inverse of effective mass. Later, Feynman looked at this problem using path integral approach of quantum mechanics by introducing quantized vortex sinks to which Vc in agreement with experimental results. He also got right dependence of Vc on channel geometry, which is beyond the scope of this course. So, students, let us summarize what we have learnt in this module. We have learnt that a photon gas is a massless boson gas with chemical potential 0, with Bose distribution function taking the form F epsilon is equal to 1 upon e raised to power epsilon upon kBt minus 1. We learned that the blackbody cavity can be treated as filled with a Bose gas of identical particles called photons corresponding to quanta of electromagnetic radiation with two transverse polarization modes. We learned that how using photon gas model for the blackbody radiation, Planck's law can be derived with spectral density delta x is equal to x cube divided by e raised to power x minus 1, where x is equal to h bar omega by kBt, which in the limit x very much less than 1, that is long wavelength limit, reduces to delta x is equal to x square. The Rayleigh Jeans approximation, and in the limit x very much greater than 1, short wavelength limit, reduces to Wien's approximation, which is delta x is equal to x cube e raised to power minus x. We learned that energy density of the blackbody cavity radiation is proportional to fourth power of temperature. We learned that emissive power, that is energy radiated per unit area per unit time, follows Stefan-Boltzmann law Rb is equal to sigma T power 4, where sigma is equal to C kb raised to power 4 divided by 4 h cube C cube multiplied by pi raised to power 2 divided by 15, which is called Stephan's constant. We learned that there is a characteristic maxima in energy density of radiation. As the temperature increases, maxima shifts to higher frequencies, representing Wien's displacement law. That pressure of the blackbody cavity radiation is 1/3 of the energy density. We also learned to derive thermodynamic properties of the photon gas, which are Helmholtz free energy, entropy, specific heat at constant volume, adiabat of a photon gas. That a crystalline solid can be treated as collection of quanta of sound energy called phonons, so that thermal vibrations of a lattice are reduced to an ideal gas of phonons, which are bosons enclosed in a space occupied by the volume of the crystal. Phonons are the quasi-particles associated with the quantization of the elastic vibrations of atoms of a solid about their mean position. We also learned that like a gas of photons, phonon gas also doesn't have quasi-particle number conservation, which can be created and annihilated, and hence chemical potential of a phonon gas is 0. The distinction between Einstein's model of a solid and Debays's model of a solid was seen to derive the phonon spectrum, also called Debye spectrum, in which g omega is proportional to omega square. Internal energy and specific heat of a solid in the form of T cube law at low temperatures was also derived. We also learnt about salient features of phase diagram of liquid helium-4, such as transition from stable liquid helium-1 phase above transition temperature to liquid helium-2 phase below transition temperature. We learned about a host of typical characteristic properties of liquid helium-2 with lambda transition in specific heat, very large heat conductivity, zero viscosity below critical velocity, creeping of liquid helium-2 in superfluid phase along the walls of the container, Andronikishvili's experimental evidence that helium-2 below transition temperature has two fluid components, namely normal and superfluid. We also learnt about two fluid model of Tissa for helium-2, which treats helium-2 as a mixture of non-Bose condensed phase with non-zero viscosity and normal mass density rho n, and Bose condensed phase with zero viscosity and mass density rho s, the so-called superfluid component of the mixture. We also learned that qualitatively Thisa's two-fluid model from thermodynamic consideration explains various properties such as fountain effect and mechano-caloric effect, but failed to account for zero viscosity or superfluidity. We learned that without treating helium-2 as a mixture of known Bose condensed phase and Bose condensed phase, Landau proposed a two-fluid model such that normal fluid consists of helium-4 atoms in thermally low-lying excited state, whereas superfluid consists of helium-4 atoms condensed in the ground state. We learned that Landau proposed for the low-lying excitations spectrum of helium-2 a phenomenological model such that the spectrum for k less than k0 is phonon-like, that is linear, whereas part of the spectrum at k is equal to k0 was given the name Proton-like, which is a quasi-particle with sigma as its effective mass and requires the minimum energy delta for its creation, that is, has to cross an energy gap of delta for its creation such that h bar omega k is equal to h bar ck for k very much less than k0 and is equal to delta plus h bar square k minus k naught whole square divided by 2 sigma at k approximately equal to k0. We learned that since energy spectrum of helium-2 is continuous, phonons and rotons follow Bose-Einstein statistics. Also, like photons, their number is not conserved and hence have chemical potential mu is equal to 0. We also learned to derive thermodynamic properties of the phonon-roton Bose gas system by using Bose statistics, namely the internal energy, specific heat, equilibrium number of rotons, Helmholtz free energy, entropy, internal energy, and specific heat. That inertial mass density of phonons, ρ0 phonon, and rotons, ρ0 roton, is a very interesting parameter to study and helps to determine which contribution becomes dominant at which temperatures to contribute to normal density of fluid. That temperature at which normal density of the fluid becomes equal to actual fluid density of helium corresponds to critical temperature at which transition from helium-2 to helium-1 takes place. We learned that there is a critical velocity below which the fluid has a superfluid behavior known as superflow. We also learned that an ideal Bose gas can show Bose-Einstein condensation, but it cannot show superfluidity. For superfluidity to be there, Bose gas must be non-ideal. Thank you.